Carbapenem-resistant bacteria, or so-called superbugs, are antibiotic-resistant bacteria that are mainly spread in hospitals. The current gold standards for testing delay the adoption of life-saving treatments, resulting in a dire 40 to 70% mortality rates in Southeast Asia. We followed a user-centric approach when developing the microRDT test. This device aims to increase testing efficiency while still maintaining clinical significance. This is a microfluidic nucleic acid lateral flow assay that detects the three most prevalent strains of CRE in Southeast Asia. Real-time epidemiological tracking is also provided via an online platform. In order to test for CRE, a whole blood sample is first taken from the patient and loaded onto the device. Through the use of blood separators, blood cells are removed to reduce undesirable red coloration and eliminate interference from intracellular material, which may affect the results and readouts of the test. MF1 bound glass fiber paper is used to optimize flow rates and plasma yield. This paper-based filtration system also reduces the cost of manufacture. As whole blood travels through the filtration system, large particles and cells are trapped on and within the glass fiber matrix. We also implemented a 3D printed channel with a square-shaped loading platform to increase absorption efficiency. This channel also prevents the blood sample from leaking out. The filtered plasma then flows into the amplification module. Since the DNA in the plasma sample is below the detection limit, the specific sequences of antibiotic resistance are amplified using a technique called recombinase polymerase amplification, or RPA. Blood plasma flows into the chambers where it combines with the reagents necessary for the reaction. After 20 minutes, the reaction is complete, resulting in plasma with amplified DNA to flow onto the conjugate pad. This isothermal technique allows amplification without a thermal cycler, reducing costs and equipment. RPA is easily transportable, user-friendly, highly sensitive, and generates results rapidly within 20 minutes. It is thus ideally suited to point-of-care settings with minimal resources. This module is 3D printed in plastic with a lightweight and low-cost design. The chambers maintain sterility, prevent leakage, and allow control of the reaction. The housing provides stability and support for the structure. A heat pad under the conjugate provides the necessary temperature for the reaction. The amplified product travels through the conjugate pad, which contains cyber-green DNA stain. The fluorescent intensity is proportional to the concentration of amplified products, allowing for quantification. This information can be used to increase therapeutic effectiveness. From there, it flows along a nitrocellulose membrane on which 3 test lines are immobilized, one for each CRE strain. These test lines consist of unique streptavidin biotinylated DNA single-strand probes, which are complementary to the tail of the DNA primers. As the DNA with the specific tails pass the test lines, they hybridize, forming a green line. These probes decrease the cost per unit and make its price more suitable for a one-time use device. The main advantage of using nucleic acid detection is that patients who have been infected can be diagnosed before they start producing antibodies. This information can be used to significantly limit the transmission rate. Finally, users take a photo of the test strip. The result is analyzed with a simple and intuitive web app. Users can navigate to the Results tab, select a picture of their device, and click a button which launches an image analysis script. This was developed using large printed mock-up strips, which means that the threshold parameters will need to be recalibrated to the strip dimensions and pixel color values of the final product. The readout is fluorescent, so in a further version we would make the software able to control the user's camera flash and include an excitation filter with the device. The program outputs the validity of the test and the results for each target strain of CRE. In the future, it will also provide possible therapeutic strategies. It will additionally store and display the location of positive cases, contributing to a monitoring network for the progression of CRE infections. Moving on to safety, each device will be covered in a plastic laminate casing and individually wrapped in a sterile pouch, only to be opened at the time of use to prevent contamination. Once a test is completed, it must be treated as biohazardous waste and put in a designated waste bin where it can then be sent for incineration. Furthermore, in terms of safety with regards to the app, we are looking to follow the GDPR data privacy laws as they are seen to be one of the strictest regulations. There is always potential for further improvement and optimization. All CRE strains could be added to our test, allowing all countries to identify and treat their respective dominating strains. Also, a mobile app could be developed to notify the medical personnel in close contact with patients who have entered a positive test result, which would be useful in a hospital setting. This would allow for immediate intervention to prevent the spread of CRE bacteria to other vulnerable patients. The data from all users would be anonymized, complying with patient confidentiality rules. As the test provides a quantifiable readout of the extent of an infection, it can also lead to improved modeling of the epidemiology of the bacteria. Hence, collected data along with the outcomes of the patients can be analysed by clinicians on a global scale in order to determine the most successful methods of treatment for every stage of infection for a given strain. To conclude, the micro-RDT test will revolutionise CRE detection and help us prevent the global spread of CRE. Thanks for listening.